at transformations of exponential functions. So our transformations of these type of functions work the same way as for any function. So taking into account what we learned about how to transform quadratics and other functions, we're going to do the same with exponential functions. Before we do that, we're just going to review some of the key properties of an exponential function. So taking a look at our function y equals, or f at x equals 2 to the power of x. Well, we can graph this very quickly. So we're going to graph the base function first. So we know, as we talked about the other day, that our y-intercept is going to be 1 because anything to the power of 0 is equal to 1. Well, we also want to think about some more key points. And what we can do is think about our key points as far as subbing in our values of x. So if we subbed -1 in for x into that function, we get 1/2. So another point we have on our base function is -1 and 1/2. Then we start to put in our positive values. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. So there's some key points that we can use to graph our function very easily. Now on the negative side, we know that that function is going to get closer and closer and closer to a y value of 0, but it's never going to cross it, which means that our asymptote of y equals 0 is placed here. We know it's never going to touch the x-axis, so we have an asymptote of which our equation for that is y equals 0. So we have some key points that we want to think about now as to our transformations. And we can use those points and alter them, or we can also take a look at points on our graph and see how they are altered as well. So in our function notation, we know that anything inside with x is going to shift left or right. And remember, if it is -6 in there, it was a positive value that went in there, so the whole thing is going to shift to the right 6 units. The +5 at the end shifts up or down, and positive value means it's going to go up 5 units. So we can take our points, point by point, and shift them right 6, up 5. So this point here goes 1, 2, 3, 4, 5, 6 to the right, and up 5, which means we're going to get to 5.5. So our new point is there. 1 shifts over to 6 and up 5, which becomes 6 and 6. 1 and 2, we shift right to the 7, and up 5 means it goes up to 7. And so on and so forth. Next one, right 6, up 5. And we also know that our asymptote also goes up 5. So that is going to shift up 5 units to y equals 5. So we can see as well where our line is going to approach our asymptote but never touch. So one more point here, 8, 3 and 8 will go to 9 and 13. And now we have our graph to plot. Okay, and as always, we want to make sure that we label with our equation. So y equals f at x minus 6 plus 5. And sorry, my 5 is not going to go on the end there. And our original y equals 2 at x. Now, the other thing we can also do is think about, as I said, moving our key points. So if we think about those points that we plotted, we had -1 and 1/2, 0 and 1, 1 and 2, 2 and 4, and 3 and 8. Now, where our points were, x and y, are going to become, we're adding 6 to our x values, and we're also adding to our y values a value of 5. So we can actually calculate our points and then plot them. So we're going to have -1 plus 6 gives us 5, and 5.5. We get 6 and 6. We get 7 and 7. We get 8 and 9. And we get 9 and 13. So we can actually get these points here and then plot them, and we notice that they are in the same spot that we have plotted our points here. Okay, so either way, using our base graph and actually shifting our points appropriately, or plotting our key points, coming up with our key points, and changing them accordingly from what we have up here. Next one, we have y equals 3f at -x. So again, thinking about what our base graph was, or key points, either way, and we know that our transformations, we're going to have a vertical stretch by a factor of 3. And sorry, that's not very neat, but vertical stretch by factor of 3. And our negative in front of the x means that we're going to have a reflection, and this is going to change our x values from positive to negative and negative to positive. So we're going to have a horizontal reflection. Or in the y-axis. So again, we can, if we want to, use our base graph. So we could plot our base graph really quickly. -1.5, 1 and 1, 1 and 2, 2 and 4, 3 and 8. And we can alter our points accordingly from there. Or we can take our key points, changing them accordingly. So what would happen to our key points here is that we're going to have x times -1, and we're going to have 3y. So 3 times as big of values for y. So again, our -1.5, 0 and 1, 1 and 2, 2 and 4, and 3 and 8, and we're going to change them. So, going to become 1 and 1.5. 0 stays as 0, and 3, -1 and 6, -2 and 12, and -3 and 24, which we realize are not going to fit. The last couple, or the last one, is not going to fit on our graph, but that's okay. So we are going to now graph our transformation. So looking at 1 and 1.5, 0 and 3, -1 and 6, -2 and 12. So we can see that, first of all, our asymptote of y equals 0 hasn't changed. There's nothing at the end here to change or shift that, so it still stays that way. And our graph is going to approach that asymptote. So we're still going to get closer and closer. We just know that we have a stretch and a reflection, meaning that we have our graph of our transformation. Now again, we could have taken those points. If we looked at our point here, it's going to stretch to 1.5, but then reflect around the y-axis. 0 and 1 stretches to 0 and 3. 1 and 2 stretches to 6, but then reflects around the x-axis. So it moves up and over. And 2 and 4 again stretches to 12, but then reflects around the y-axis. Okay. Now, example number 2, this time we have a base function of y equals 4 to the power of x, or f at x equals 4 to the power of x. And what we want to graph is g at x, which is equal to 4 to the power of 1/2 x minus 6. So again, thinking about how our values are going to change, and we can think about key points as well. So if we have f at x, base function, is 4 to the power of x, thinking about key points. Again, knowing our base function, we want to have 1 in our negative, so we're going to have -1. 4 to the power of -1 is 1/4. Remember that flips that. 0 and 1, 1 and 4, 2 and 16. Okay, 3 and 64 isn't going to fit on our graph anyways, so we're going to leave it at that. Now, looking at how these are going to change, we know that, and sorry, I'm going to write this down at the bottom here, didn't leave a whole lot of space. Our y equals, or our f at x equals 4 to the 1/2 x minus 6. Our 1/2 here is with our x, so it's going to alter our x values. Our x values are going to change accordingly. Now remember, 1/2 means that that is going to be a stretch, does the opposite, by a factor of 2. So it's going to be twice as wide. So this is horizontally. Our -6 means that it is going to translate or shift down 6 units. So when we look at our key points, we are going to change our x and y. We're going to multiply our x by 2, and we're going to subtract 6 from y from each of our key points. So multiplying by 2, we get -2. We're going to subtract 6 from y, which is going to give us -5 3/4. 0 and -6. 2 and -2. And 4 and 10. So, first of all, thinking about our asymptote of our base graph was y equals 0. It is now going to shift down to y equals -6. So we know that's where our graph is going to approach. So if we start plotting our points now, we're going to have -2 and -5 3/4. So very close to our asymptote. 0 and -6. Sorry, should be -5 there. Notice it went past the asymptote, which told me right away something was wrong and I want to fix that. So that should be -5, 0 and -5, 2 and -2, and 4 and 10. So we have our graph of our transformation. And that's y equals, g at x equals (4 to the power of 1/2 x minus 6). And we can double check that it makes sense. We do have a shift down of 6. It's twice as wide. Our x's are 2 apart rather than 1 apart, the values that we used, and we have our graph. And in this case, if we use our key points, we don't have to graph the base graph. We can go straight to the graph. Now, example 3, without graphing, we want to state the domain and range of y equals -10 to the power of x plus 2. Well, we want to think about our base graph. So our base graph here, so we're always looking at how it compares to our base graph. So thinking about our base graph here of y equals 10 to the power of x. Well, our domain and range, remember our domain of our functions, we can sub any value in there for x as an exponent. Now, the range, though, did have its limit. For our base function, we know that y such that y has to be greater than and not equal to, just greater than 0, and can be any real number from there. Well, now we take a look at how has our function changed. So our plus 2 shifts our base function up 2 units, and our -10 is going to reflect in the x-axis, or a vertical reflection, which changes. So the reflection in the x-axis isn't going to change our domain. Our domain of any function is still going to be any real number. So our domain stays any real number. Our range, though, our limits on our y's, we see that it moves up 2 units, which changes our y values. And the reflection means that it's going to open down from there. So we now have a y value that has to be smaller than or equal to 2 and can be any real number. And if we just think about quickly graphically, our graph of y equals 10 to the power of x would still have a y-intercept of 1, and it would go up from here. Well, our shifting down 2 makes it look like this, and then our reflection means that it has to go the other way. So it does make sense that our asymptote is now at y equals, should be up 2 and should be at y equals 2. So our graph should be up here. Okay, sorry about that. So shifting up 2 and reflecting means that our asymptote is up here at y equals 2. Okay, and so you have some questions to practice. As always, just make sure if you have